All right, so hi everybody, welcome back. Today we're going to be finishing up our chapter 35 lecture on diffraction and polarization of light. So by the end of this video, we'll be completely finished with all the topics from chapter 35 that I wanted to cover. And the next one that I wanted to discuss is limits of resolution. So let's get into this. So first of all, when we talk about the resolution of an optical instrument, and this can be anything from a camera to the human eye, to a telescope, to a microscope. When we talk about the resolution of that instrument, we're referring to its ability to distinguish two nearby sources of light as separate objects. Okay, so if I have two nearby sources of light, and I can actually tell that they're two different objects and the light is not just blending together, then I'm resolving those objects. So the resolution is the ability to tell two objects apart, even though they're close together in our field of view. So there are a lot of different factors that can limit the resolution of an optical instrument, because of course, you can never have perfect resolution. There's always going to be a limit to your ability to resolve things with an optical instrument. So some of the factors that go into this are things like lens and mirror aberrations. So if your instrument consists of lenses and mirrors, if they're not in the right shape, if there are some defects on the surface of the mirror or the lens has defects on it, those are what we call aberrations, and those can affect your ability to resolve things. And whenever we use an optical instrument on Earth, we're going to be dealing with atmospheric blurring. The idea is when light travels through the air can distort that light, particularly if there's a lot of turbulence in the air, okay? That's atmospheric blurring. This is especially important in astronomy when we use ground-based telescopes. So if I set up a telescope in my backyard and I try to observe a star with that, well, the light from the star has to travel all the way through Earth's atmosphere to get to my telescope. On the way, you can get a great deal of atmospheric blurring, and again, that can affect your resolution. The more atmospheric blurring you're experiencing, the more poor your resolution is going to be. Another important factor is the spacing of detector elements. So in a camera, we're talking about the pixels on the camera. Anything smaller than a pixel on your camera just can't be resolved. We can only resolve things as small as the smallest detector element on your camera. Or if we're talking about the eye, these would be the rods and the cones in your eye. Any feature that's smaller than that, we're just not going to be able to see it with your eye. And so lastly, we have diffraction. So remember, in general, diffraction is when a wave goes through an opening, and then after going through that opening, the wave spreads out. Now, of course, this happens for light. If you have a light wave going through the pupil of your eye, or into a camera, or into a telescope, whatever the case may be, whenever light enters an optical instrument, it's going to diffract. And that's not something you can engineer around, okay? That's always going to happen if you have light entering an optical instrument. It's simply due to the wave nature of light. You can't engineer around this. So always, our ability to resolve objects is going to be limited by diffraction. This is going to limit the resolution of any optical instrument. So we're going to focus on this in this section. So in particular, we're going to look at diffraction through a circular aperture. In other words, the opening that the light goes through, that's what we call our aperture, has a circular shape. So this can be anything from the pupil of your eye to the aperture of a camera. Typically, these are going to be circular openings. So we want to understand how light diffracts when it goes through a circular opening. Well, this is basically what it looks like. We have a diffraction pattern that doesn't consist of little spots on a screen, but instead it consists of a central bright disk, which we call the airy disk, and then that's surrounded by several bright rings, which we call the airy rings. Okay, that's the diffraction pattern we get when light goes through a circular aperture. So we're not going to derive this equation. We're just going to quote the result and then see what we can do with this. The size of this airy disk is given by theta is equal to 1.22 lambda over d. So let's explain what this means. Theta is what we call the angular half-width of the disk. So if this is our aperture where the light is going through, and then this is our diffraction pattern, and this is the very center of it, this is just that central disk, which we call the airy disk. The angle theta goes from the center of that disk out to the edge. So it's half of the width of the disk, and we're giving that as an angle. So that's what theta is referring to, the angular half-width of the airy disk. Now lambda, of course, is the wavelength of the light, and then capital D is the diameter of the circular aperture. So basically, theta tells us how big that airy disk is, so it tells us how much the light is spreading out. We can calculate that simply based on the wavelength of the light and the diameter of the aperture. So notice one thing about this. The smaller d is, the smaller the aperture, the bigger theta is. Okay, so the smaller the opening the light goes through, the more it diffracts, the more it spreads out. That's important to see in this equation. And I guess the last thing to mention here is when you calculate the angle this way, it comes out in radians. Okay, so this is how you calculate the angle in radians. Okay, so I'm going to show you another experiment very briefly. On the very left-hand side of this track, we have our red laser, which produces light with a wavelength of 635 nanometers. We're going to send that light through a small circular opening. So on this screen here, we can adjust the setting so that the light is going through a small circular opening. And then we can see what happens when we project the light that goes through the opening onto a piece of paper. Again, the room lights are on, so it's a little bit hard to see what the overall pattern is. So let's cut the lights off and see what happens, see what's getting projected onto this screen over here. So here's what it looks like. You can see that at the very center, we have a bright disk. That's what we call the airy disk. But surrounding that are a series of rings, and we call those the airy rings. And there's a gap in between each of the rings, so a minimum in the diffraction pattern is what you see in between each ring. So that's what it looks like when you send coherent light through a small circular opening. You get this diffraction pattern. So one place where the effects of diffraction become very obvious is when we take an image of a star using a telescope. Now, typically stars are so far away that we can't really resolve their size. Essentially, they're just points of light. But if you take a look at this image taken by the Hubble Space Telescope of a group of stars, we don't just see points of light in the image. Instead, what we see is a central bright disk surrounded by a series of rings which get less and less bright as you go out. So that would be the airy disk surrounded by the airy rings. That's exactly what we'd expect to see given that light is diffracting through a circular aperture. The light that we see here had to come in through the circular aperture of the telescope in order to actually be seen. So that's the effect of diffraction through a circular aperture. But in addition to that, we also have what are called the diffraction spikes. These are the bright lines that are coming off the central bright spot of each star. Now, the reason for that is when light comes into the telescope through the aperture of the telescope, it has to diffract around the struts that hold up the secondary mirror of the telescope. So here's the idea. This is the aperture of the telescope. This is the opening that the light comes in through. After it comes in through there, it goes and reflects off the primary mirror, which is this large mirror in the back of the telescope. It reflects off that towards the secondary mirror, which is right here, and then out through a small opening in the primary mirror where we can read it out using a CCD or an eyepiece or something like that. But the point is, the light has to go around the barriers that are presented by these struts holding up the secondary mirror. By diffracting around those struts, we end up getting these diffraction spikes that you see here in the images. That's why those are present. And so that takes us to the Rayleigh criterion. Now, here's the idea behind the Rayleigh criterion. Let's say we have 2 point sources of light. So we have a source of light over here and another one over here. And we're observing these sources using some kind of optical instrument. It could be a camera, it could be your eye, it could be anything, but the point is the light is coming through a circular aperture. So after the light goes through the aperture, it diffracts. So you don't just see a point of light, you see the airy disk and the airy rings around it for each one of the sources. So the idea is, if the sources are far enough apart, if there's a big enough angle between them, then these diffraction patterns won't overlap, so you'll be able to distinguish one object from the other. On the other hand, if they're way too close together, then the diffraction patterns will be right on top of each other, and the light will just basically blur together. There's no way to tell that these are actually 2 separate objects. So the Rayleigh criterion gives us a way of saying whether or not we can resolve the 2 objects, okay? So here's what the Rayleigh criterion says. 2 sources are just barely resolvable if the center of the diffraction pattern of one source overlaps with the first diffraction minimum of the other source. So here's the Rayleigh criterion in a picture. We have one source where the diffraction maximum in the very center is right here. So here's the middle of that diffraction maximum. Our second source has its first minimum right there at that same point. So as long as that's as close as they get and they don't get any closer, then we can resolve them. If they get any closer together than that, we can't resolve them. If they're further apart than that, then that's great. We can still resolve them. So the Rayleigh criterion is that borderline case where we just barely are able to resolve the 2 sources. So the picture that you should be having in your mind is we have a source over here, S1, another source of light over here, S2. There's some kind of angular separation between them, some kind of theta, some angular separation there. In order to actually resolve the 2 objects, the angular separation must be greater than a certain minimum value. That minimum value is 1.22 times lambda over d. Okay, this is what we saw earlier for the width of the airy disk. It's 1.22 times lambda over d. If the angle is bigger than that, we can resolve it. If the angle is smaller than that, then we can't resolve the 2 objects. Again, lambda is the wavelength of the light, and d is the diameter of the aperture that the light is going through. Okay, so this is the Rayleigh criterion. Now, let's do an example with this, where we see what the resolution limits of the human eye are. So suppose that you're flying in a plane at an altitude of 12 kilometers above the ground, and you're looking down straight towards the ground. The pupil of your eye has a diameter of 3 millimeters, let's say, and the wavelength of the light that is entering your eye is 550 nanometers. So the question here is, what is the smallest feature on the ground that you can resolve with the naked eye? What is the smallest object that you can actually resolve just using your eye? So let's work it out. So let's start by drawing a picture of what's going on. We have the eye. This is the person looking down at the ground. And they're looking at some type of object. So, it doesn't really matter what the object is, but it has a certain size from one end to the other. Let's call that size S. Now, we'll draw a line going from the eye to one side of the object, and another line going from the eye to the other side of the object like this. And that defines the angle, the angular size of the object, theta. So we'll also note that there's a certain height above the ground. We'll call that h. That's the 12-kilometer distance. And so that will go there. Now, we can take the triangle that we drew in that diagram and cut it in half. So I'm going to draw a line that cuts the triangle in half down the middle. So now this angle is half of theta. It's theta over 2. This side is h, and this side is s over 2. Okay, it's half the size of the object now, but we have a right angle over here. Okay, so if we take the tangent of the angle, which is theta over 2 in this diagram, that's the opposite side of the triangle over the adjacent side. Well, the opposite side is s over 2. The adjacent side is h. And we want to solve for s. S, in this case, will equal 2 times h times tangent of theta over 2. Okay. Now, let's remember that as long as we have small angles, then tangent is approximately equal to sine. And actually, I should put an angle in there. So tangent of some angle, let's say alpha, is approximately equal to the sine of that angle, which is approximately just equal to the angle itself if it's measured in radians. Okay? So let's use the small angle approximation here. S is approximately equal to 2h times tangent of theta over 2. But if the angle is small, then tangent of theta over 2 is approximately just equal to theta over 2, just the angle itself. And the factors of 2 will cancel, just giving us theta times h. Okay? Another way of seeing this is, if we go back to the original picture, if the angle is small, then this distance s can be considered to approximately be an arc length on a circle. So remember, arc lengths are given by an angle times a radius. So in this case, the radius would be h, the angle would be theta, so theta times h equals the arc length s. Okay, that's another way of seeing the result, that s is approximately equal to theta times h. Okay, so now let's use the Rayleigh criterion. Because the smallest thing we can resolve has an angular size theta min equal to 1.22 times lambda over d. That's what we should use for the angle. So that means S min is equal to 1.22 times lambda times h divided by d. Okay, so just combining these two ideas. Now, we have 1.22. The wavelength of the light is 550 nanometers. 550 times 10 to the minus 9 meters. And then we have h, which is 12 kilometers, or 12 times 10 to the 3 meters, divided by d. That's the diameter of the aperture, that's the pupil of your eye, has a diameter of 3.0 millimeters, which is 10 to the minus 3 meters. So this comes out to about 2.7 meters. Okay, so that's the answer. And again, what this means is if you're flying 12 kilometers above the ground, the smallest thing that you'll be able to resolve on the ground has a size of about 2.7 meters, so roughly speaking, the size of a car in that range. So let's take a look at another example. The resolution of ground-based telescopes is typically limited by atmospheric blurring, okay? Because you have to look through Earth's atmosphere to see out into space if you have a ground-based telescope. Now, under optimal weather conditions, an angular resolution of about 2 times 10 to the minus 6 radians can be achieved with the best ground-based telescopes. On the other hand, the resolution of a space-based telescope is only limited by diffraction, because a telescope that's out in space, like the Hubble Space Telescope, doesn't have to look through the atmosphere. So it's only diffraction that limits the resolution. So the opening diameter of the Hubble Space Telescope is 2.4 meters. For light with a wavelength of 550 nanometers, what is the angular resolution of the Hubble Space Telescope? And as a follow-up, how much better is that angular resolution compared to the best ground-based telescopes? So pause the video, try to work this out, and then we'll go through it together. Okay, so when we refer to the angular resolution, we're talking about the smallest angle that can be resolved. And so, of course, this is going to be given by the Rayleigh criterion. Okay, so theta min, our angular resolution, is given by 1.22 lambda over d, where this is measured in radians. And for the Hubble Space Telescope, we have 1.22. The lambda we're going to use is 550 10 to the minus 9 meters. By the way, that corresponds to green light. So 550 nanometers is 550 10 to the minus 9 meters divided by d. That's the size of the aperture, the circular aperture of this the Hubble Space Telescope. So that's 2.4 meters. Okay, so that gives us 2.8 times 10 to the minus 7 radians. And again, I want to point something out, that when it comes to the angular resolution, theta min, it's inversely proportional to d, meaning the bigger the aperture, the bigger the telescope we build, the better its resolution will be, the smaller the angles we can resolve. But anyway, if we compare this to ground-based telescopes, theta min for the Hubble Space Telescope divided by theta min for the best ground-based telescopes. So for HST, we have 2.8 times 10 to the minus 7 radians. For the best ground-based telescopes, we have 2 times 10 to the minus 6 radians approximately. So that ratio is about 14, meaning you can get about 14 times better resolution by putting your telescope up in space and avoiding looking through the atmosphere. Okay, that's the idea. So let's do another example. This one deals with the dispersion of a beam. So the idea here is diffraction makes it impossible to produce a perfectly collimated beam of light. In other words, it's impossible to make a beam of light that's only going in one direction. Any beam of light is going to spread out to some extent. There's going to be some kind of opening angle alpha to the beam. Okay, so that's what's shown here. Now, let's suppose that we have a dish with a diameter d is equal to 2.65 meters, and it emits radio waves that have a wavelength lambda, which is equal to 12.5 centimeters. The question is, what is the minimum opening angle of the beam? What is alpha in units of radians? And then we'll also calculate it in units of degrees. So let's work it out. Okay, let's start by drawing a picture of what's going on here. We have our radio dish. This is our circular aperture. And then we have a beam coming out of there. And the beam opens up at some angle, which we want to figure out, which is alpha. Now, what we really mean by this is that since the beam is going through a circular aperture, we get this diffraction pattern where at the very center, we have the airy disk. And the airy disk contains the vast majority of the energy of this beam. So what we are saying is the angle that the airy disk spans is alpha, okay? So if we take half of that angle, so in other words, we go from the center of the disk out to the edge, that's theta. And what we saw earlier is that theta for the airy disk, that's what we call the angular half width, because we're going from the center out to the edge, so it's half of the full width. That's equal to 1.22 lambda over d. And remember, if we calculate it this way, it comes out in radians. So we have 1.22. Lambda is 12.5 centimeters, which is 12.5 times 10 to the minus 2 meters. Divide that by d. The diameter of the dish is 2.65 meters. Now, if you calculate that, it comes out to 0.05755 radians. But we want to convert that to degrees really quick. So multiply by the conversion factor. 2 pi radians on the bottom is equivalent to 360 degrees on top. So this is 3.297 degrees, keeping 3 sig figs, by the way. But alpha, if we go back to the picture, is 2 times theta. So we want to double that. 2 times 3.297 degrees. That's equal to 6.594 degrees. And then if we just keep 3 sig figs on that, about 6.59 degrees. So that's at least how much this beam has to open up, and that's given by the fact that it's diffracting through the circular aperture. And so that takes us to the last topic of this lecture, which is polarization of light. So let's get into this. Now, polarization refers to the direction of the oscillations in a transverse wave. So let's give an example here. Let's say we have a wave on a string. That would be an example of a transverse wave. So even if we know which way the wave is traveling, let's say we know it's traveling this way down the length of the string, that doesn't necessarily tell us which way the string is oscillating. So you could shake the rope up and down like this, so the oscillations are vertical, or you could be shaking the rope from side to side like this, so the oscillations are horizontal. Either way, you're still going to get a wave traveling this way down the length of the string. And so that's the idea behind polarization. So if we have a transverse wave, there are different directions that it can be oscillating in, even if we know which direction the wave is actually traveling in. So if we take a look at the first example I gave you, where the string is shaking up and down, that would be called a vertically polarized wave. In the example I gave you where the string is shaking back and forth, we would call that a horizontally polarized wave. So the polarization gives you the direction that the wave is oscillating in. Now, closely related to this is the idea of a polarizing filter. So a polarizing filter only lets waves with a particular type of polarization pass through. Waves that are polarized perpendicular to that will be blocked. So let me give you an example. If we're taking a wave on a string as our example, we can create a polarizing filter just by creating a slit that the wave has to pass through. So if the slit is oriented vertically like this, then if I have a vertically polarized wave, it's perfectly free to pass through. There's no problem. And on the other hand, if we have a horizontally polarized wave like this, then it won't be able to get through the filter because the wave on the string needs to shake back and forth in the horizontal direction, but that type of motion is going to be blocked by the slit. So this wave is not going to be able to get through. That's the idea behind a polarizing filter. Certain types of waves with certain polarizations will be able to get through. Other types of polarizations won't be able to get through. Now, let's see how we can apply this idea of polarization to a light wave. Remember, light can be thought of as an electromagnetic wave. It consists of an oscillating electric field, which is given by E, and an oscillating magnetic field, which is given by B. So I showed you this animation of an electromagnetic wave before, but it's worth taking a look at again. So in blue, we have the electric field, which oscillates up and down along the y-axis. In red, we have the magnetic field B, which oscillates along the z-axis. And then the wave itself is traveling in the x direction. So this is what it looks like when the electromagnetic wave moves by. So this is a transverse wave. Obviously, we have the oscillations happening perpendicular to the motion of the wave, but we have E or B, which we can choose to define our polarization. So by convention, the polarization of a light wave is given by the direction of the electric field. So when we talk about the polarization of the light wave, we're talking about which way the electric field is oscillating. So in this example, it's polarized along the y-axis, okay, because it's oscillating up and down along the y-axis. Now, on a diagram, we will indicate the direction of the polarization of a light wave using an arrow. So this up-down arrow is telling us that the E field is oscillating up and down in this direction. That's how we indicate the direction of polarization on the diagram. Okay, so how do polarizing filters work when it comes to light waves? How do we build a filter that only lets light with certain polarizations go through and blocks other polarizations? And so this is how it works. A polarizing filter for light is basically just made of very long molecules that are all arranged parallel to one another. So if light comes in that's polarized parallel to the length of those molecules, it's mostly going to be absorbed. So here's the idea behind that. Let's say I build the filter so that the long molecules are laid out like this from left to right across the filter. And then let's say that I have a light wave coming in that's polarized horizontally like this. So the E field is oscillating from left to right like this. That's going to cause electrons in this very long molecule to oscillate back and forth in that same direction. That's what the electric field will do. That's going to eat up the energy of this light wave. Okay, the energy of this light wave is going to go into energy of these oscillating molecules. So in other words, very little of that light wave is actually going to be transmitted. Its energy is mostly going to be absorbed. On the other hand, if we have light that's polarized perpendicular to the length of those molecules, that's mostly going to go through. So if this shows the length of the molecules, again, going from left to right, but this time we have a light wave that's polarized vertically, so the E field is oscillating up and down like this, well, the electrons don't really have any room to oscillate up and down in that molecule, so very little of the energy of the light wave is going to be absorbed. It's mostly going to pass through. So that's how we block polarizations of a certain type and let other polarizations go through, just using these long molecules. So ideally, all of the light that's polarized parallel to our transmission axis is going to go through the filter. So for the filter, we have what's called a transmission axis. If we're polarized right along that axis, then the light should all go through. And then anything polarized perpendicular to that axis is going to be blocked. Okay? That's ideally how a filter should work. And so that takes us to Malice's law. Malice's law tells us what happens when we have a polarized light wave going through a polarizing filter. So a little bit of terminology. The light wave that's coming in is called the incident light wave. The light wave that comes out of the filter is the transmitted light wave. So the first thing to note is that when polarized light goes through a polarizing filter, the transmitted light is polarized, but along the axis of the filter. So whichever way we choose to orient this axis, that's going to be the direction of the polarization of this outgoing wave. Malice's law also tells us how to relate the intensity of these two waves. So IT is the intensity of the transmitted wave, II is the intensity of the incident wave, and theta is the angle between the polarization of the incident light wave and the filter's transmission axis. So we have a certain direction of the polarization of the incident light wave. The filter has its axis oriented in a certain direction, so the angle between those two directions is theta. Okay, so Malice's law tells us that IT, the intensity transmitted, is equal to II, the incident intensity, times cosine squared of theta. So what matters is the angle between the axis of the filter and the incident light wave's polarization. So let's work out these results. Okay, so let's draw a picture of what's going on. Again, to indicate that we have a polarized light wave coming in, we'll show these up and down arrows, which indicate the direction of the E field. So the E field is oscillating up and down like this. Then we have our polarizing filter. We show the direction of the transmission axis using these lines, which we draw across the filter. So that indicates the transmission axis. And this is our polarizing filter. Okay, so the incident light wave has an electric field, which is vertical in our picture, and we'll call that E initial. And then the transmission axis is in this direction, denoted by this dashed line. And there's an angle between them. That's what we call theta. So here's the thing to realize. Only some of the incident light wave is going to make it through. In other words, only the component of E that is parallel to the transmission axis is going to make it through. Okay, any component that's perpendicular to the transmission axis gets blocked by definition. So let's drop a line down onto the transmission axis like this, so that's perpendicular to it. Only this part right here that's parallel to the transmission axis is getting through. So this will be ET, the electric field that gets transmitted. So the first thing to realize is the transmitted E field is parallel to the transmission axis of the filter. That's just another way of saying once the light wave comes out of the filter, it's polarized along the axis of the filter. Okay, now what is ET in the first place? Well, ET is just EI, which is the hypotenuse of this triangle right here, times cosine of theta. Okay? Just doing a little trig, we see that ET is equal to EI cosine of theta. Now, when it comes to light waves, the intensity is proportional to the E field squared. So when it comes to a light wave, the E field is like our amplitude, because the intensity of a wave goes as amplitude squared. The E field stands in for our amplitude in this case. So I is proportional to E squared. Another way of saying that is I divided by E squared is a constant. Okay, so that means the intensity of the incident wave divided by the E field of the incident wave squared is equal to the intensity of the transmitted wave divided by the E field of the transmitted wave squared. That means the intensity transmitted is equal to the incident intensity times the E field transmitted divided by the E field incident all squared. But from up here, we have the result that the E field transmitted is the E field incident times cosine theta. So let's plug that in. II is equal to EI cosine theta divided by EI all squared. So cancel out EI, we get II cosine squared theta. That's where Malice's law comes from. Now, Malice's law is not the whole story, because Malice's law only tells you what happens when we have polarized light going through a filter. But there's also the possibility that you can start with unpolarized light. So unpolarized light is just a mixture of many light waves with different polarizations. So it's just a random mix of waves with different polarizations, and there's no preferred direction. There's no overall polarization to those waves. So on a diagram, we show the fact that we have a mix of many different polarizations by using a set of crossed arrows, meaning some of the light is polarized this way, some of it's polarized that way, some of it's polarized that way, and so on, so that overall there's no real direction of polarization that's preferred. So one thing we want to know is what happens when you take unpolarized light and you send it through a filter. And so in this situation, the transmitted intensity would be exactly 1/2 of the incident intensity. And the transmitted light wave that makes it through the filter is going to end up being polarized along the axis of the filter. So again, you have unpolarized light coming in. What comes out has half the intensity of the incident light, and now it is polarized along the axis of the filter. So let me show you how that works. Okay, so the thing to realize is that when we have unpolarized light, we have a mixture of waves with different polarizations. So that overall there's no preferred direction of polarization. But for each one of those waves, we'll have Malice's law apply. The transmitted intensity is equal to the incident intensity times cosine squared of theta. So next, I'm going to bring up something from calculus. Okay, you may remember this from calculus 1. The average value of a function. We can calculate the average value of a function. Let's call it f of x. So the average is denoted by these brackets here. The average of f of x is equal to 1 over xb minus xa times the integral of xa to xb, so those are the limits of integration, of f of x dx. So what I'm saying here is, if you integrate a function between 2 points, xa and xb, and then you divide out the width of that interval, which is xb minus xa, you'll get the average value of the function in the interval that you're interested in the interval from xa to xb. So let's apply that to the transmitted intensity. The average transmitted intensity of all of these different waves is, so using the same notation, we have the brackets around IT, which would be the same as the brackets around II times cosine squared theta. So according to how we calculate average values, this would be 1 over. Now, what's the range of theta values that I could have? Well, 2 pi at the top limit and 0 at the bottom limit. So I'm going to have 1 over 2 pi minus 0. And then I'll be integrating that. I'll be integrating from 0 to 2 pi of II cosine squared theta d theta. So what I have is 1 over 2 pi. I can also pull out the constant, which is II. And then I'm just going from 0 to 2 pi cosine squared of theta d theta. So I'm not going to work out the integral right now, but if you punch this into a calculator or Wolfram Alpha, you can see that this integrates to pi. So we just get pi when we perform that integral. So we have I over 2 pi times pi, which is just 1/2 times I. So what gets transmitted, if we start off with unpolarized light, is just 1/2 of the incident intensity. Okay, that's how this works. On average, only half the intensity is going to make it through. So let's do an example involving polarizing filters. So here we have unpolarized light with an intensity of 24.0 watts per square meter, which is incident on a set of 3 polarizing filters. So the light goes through each filter one after the other. By the way, an easy way to get unpolarized light is to use a standard light bulb. This would be emitting unpolarized light with no preferred direction of polarization. But the question is, what is the intensity of the light transmitted through the last filter? So how much intensity do we have coming out of that third filter? And also, in what direction is the light polarized after going through each filter? So let's work this out. So let's take each filter one at a time. So if we start with the first filter, we have unpolarized light coming in. So the transmitted intensity, let's call this I1, the intensity after going through the first filter, is 1/2 times I0, which would be the initial intensity of this unpolarized light, 24 watts per square meter. So 1/2 of that is 1/2 of 24 watts per square meter, or 12 watts per square meter. So after the first filter, the intensity is cut in half. Also, the light after going through the first filter is now polarized along the axis of the first filter. So we'll show that using an up and down facing arrow along the axis of the first filter like this. Now, when the light goes through the second filter, we don't have unpolarized light going through anymore. We have polarized light is coming in. So now, if we want to know the transmitted intensity, which I'll call I2, that's going to be given by Malice's law. So that would be the incident intensity, I1, okay, the intensity of this wave right here, times cosine squared of theta, where in particular, theta is the angle between the axis of filter number 1 and the axis of filter number 2. So that's going to be the 30-degree angle that we see in the diagram. So I have I1, 12.0 watts per square meter times cosine squared of 30 degrees. So if you work that out, it's exactly 9 watts per square meter. And now the light comes out of that second filter polarized along the axis of the second filter. And now the intensity is I2. Okay, now if we take the third filter, again, we have polarized light coming in. So it's going to be Malice's law that gives us the transmitted intensity. We'll call it I3. That's going to be I2 times cosine squared of the angle between filter number 2 and filter number 3. Let's explain this a little bit more. So again, this light wave comes out of the second filter polarized along the axis of that second filter. And then it goes through the third filter. So if this is the direction of polarization right here, What I want is the angle between that and the axis of the third filter. And so that's the angle I'm referring to as theta 2, 3 in my equation. And if we work this out, we have I2, which is 9 watts per square meter, times cosine squared. The angle in question would be 90 degrees. That's the axis of my third filter with respect to the vertical, minus 30 degrees. That's the axis of my second filter with respect to the vertical. So the difference is 90 minus 30, or 60 degrees between them. And we're taking the cosine squared of that angle. So we have 9 watts per square meter, cosine squared, 60 degrees. And if you work that out, it's 2.25 watts per square meter. So that would be the final transmitted intensity. And the outgoing light wave is going to be polarized this way, along the axis of that third filter. So perfectly horizontal. With intensity, I3 equals 2.25 watts per square meter. Okay, that's how this works. So here's a question for you guys to think about. We have unpolarized light with that same intensity of 24 watts per square meter, which is incident on a set of 3 polarizing filters. So it's basically the same setup as before. The first filter has an angle of 0 degrees relative to the vertical, so it's completely vertical. The third filter is at 90 degrees with respect to the vertical, so it's perfectly horizontal. And the second filter is going to be variable, so we can move it at any angle we want. So theta 2 is something we'll change throughout the problem. So the question is, what would the final transmitted intensity be if the second filter were set to 45 degrees, again, relative to this vertical line? What would it be if the second filter were set to 0 degrees relative to this vertical line? What if it were set to 90 degrees? And what would happen if we just removed the second filter altogether? So in each one of those scenarios, try to think of what would the transmitted intensity be. So pause the video, try to work it out, and then come back to it when you think you have your answers. Okay, so to work this out, we're going to come up with a general formula for the final transmitted intensity, and then we can just use that for all 3, or actually all 4 questions that I asked, okay? So first, we have unpolarized light, let's call the intensity I0, going through a filter. And after it goes through that first filter, the light is now polarized along the axis of the first filter, and it has some new intensity, which I'll call I1. So I1 is exactly 1/2 of I0, because when we have unpolarized light going through a polarizing filter, the intensity is cut in half. Okay, so next we have this light wave going through the second filter. After it goes through the second filter, it's polarized along the axis of the second filter, as shown in the diagram, and now the intensity is I2. So if I want to figure out what I2 is, now I need to use Malice's law, because for the second filter, we have polarized light going through a polarizing filter. And so the way this works in Malice's law is the transmitted intensity I2 is equal to the incident intensity I1 times cosine squared of an angle, which I'm going to label here as theta 1, 2. So that would be the angle between the polarization of this wave that has intensity I1 over here and the axis of the second filter. So let's label that. This angle is theta 1, 2. But since this wave is polarized along the axis of the first filter, when I'm referring to theta 1, 2, I'm really just talking about the angle between the axis of those 2 filters, the angle between the axis of filter 1 and the axis of filter 2. Let's just write that down. Angle between axis of filter 1 and axis of filter 2. Okay, so now the light goes through the third filter, and after it goes through the third filter, of course, it's polarized along the axis of that third filter, and now the intensity is I3. And when we apply Malice's law to find I3, that's I2 times cosine squared of the angle theta 2, 3, which I'll show you in the diagram is this angle right here. It's the angle between the second and the third filter. So it's the same logic as before. But let's make some substitutions. I2 is just I1 times cosine squared theta 1, 2. So we'll multiply that by cosine squared theta 2, 3. But then from the very first thing we wrote down, I1 is a half of I0. So this is a half I0 cosine squared theta 1, 2 times cosine squared theta 2, 3. So we have a series of questions that we can now answer using this sort of general formula. So in the first question, we have theta 2, the angle of our second filter relative to the vertical is 45 degrees. So that means theta 1, 2, the angle between filter 1 and filter 2 is 45 degrees. And theta 2, 3, that's going to be also 45 degrees. So we calculate I3, that's going to be 1/2 times I0, which is 24.0 watts per square meter, times cosine squared 45 degrees times cosine squared 45 degrees once again. And that will give you 3 watts per square meter. Okay, in the second example, we set theta 2 to be 0 degrees. So the second filter is perfectly vertical, just like the first filter, which means theta 1, 2 is going to be equal to 0 degrees. So there's no angle between the first and the second filter, but theta 2, 3 is going to be 90 degrees. And if you remember, cosine of 90 degrees is 0. That automatically gives you 0 transmitted intensity, because we'll have cosine of 90 in the formula. Okay, in the next case, we have theta 2 equaling 90 degrees. So that means we set the second filter so its axis is perfectly horizontal. Now that means the angle between filter 1 and 2 is 90 degrees, because one of them is completely vertical, the other is completely horizontal. And then theta 2, 3 is 0, because those are both now perfectly horizontal. But again, for the same reason as before, we're going to have a cosine 90 degrees in the equation, which is going to give us 0 transmitted intensity. So whenever you have two filters, one after another, that are at 90 degrees, you're going to get 0 transmitted intensity. Okay? And then finally, if the second filter is removed, so forget the second filter is here. We just have filter 1 and then filter 3. Well, then the transmitted intensity through filter number 3 is going to be 1/2 I0, because going through the first filter, we still cut the intensity down by a factor of 2. But then we have cosine squared of the angle between filters 1 and 3 now, okay? But here's the thing. Filter 1 and filter 3 are at 90 degrees to one another. So once again, we're going to get 0 transmitted intensity because of the fact that cosine of 90 degrees is equal to 0. So that's how these examples work out. Okay, so next I want to show you a quick demo that you can do at home using polarizing filters. So I have two polarizing filters here. If you have two pairs of sunglasses at home, you can easily recreate this experiment using your two pairs of sunglasses. So the idea is you're going to find some sort of light source. For me, I'm going to just use this overhead light, and we're going to send that light through a polarizing filter. So what's happening here, according to what we've learned in the lecture, is the intensity of the light is being cut down by a factor of 2 because we have unpolarized light going through a polarizing filter. But remember, after it comes out of this filter, the light will now be polarized along the axis of this filter. So let's keep that in mind and then add a second filter to the system. So I'm going to put the second one in front of the first, but I'm going to start where the axes are completely aligned with each other. There's 0 degrees of an angle between the two axes. So we still get plenty of light coming through, as you can see here. Okay, the intensity is pretty much the same as just with the single filter. But now I'm going to rotate this axis slowly, and you can see as I do that, the transmitted intensity basically goes to 0. Okay, it looks completely dark where you would see light coming out before. That's because I have the axes of the filters at 90 degrees to each other. Okay, so light comes out of the first filter, polarized along the axis of that filter. The second axis is now at 90 degrees to that. But if your filter is at 90 degrees to the direction of polarization, then you should get 0 transmitted intensity. And that's what we're seeing. Again, you cross the filters at 90 degrees, hold it up to the source, and essentially you're getting no light coming through. Okay, that's what we're seeing here. Okay, so we've seen that one way to create polarized light is to use a filter. If you have unpolarized light, you send it through a filter, it comes out polarized. Now, another way to create polarized light is by reflection. So the idea here is if you have unpolarized light hitting a surface and then reflecting off it, that reflected light that comes out becomes polarized, okay? And it becomes polarized along the direction that's parallel to the surface. So the picture we have in mind is we have the interface between two materials, N1 and N2 down here. And the interface between the two materials, or the surface, is shown right here. Now, to indicate that the incoming wave is unpolarized, we show that the electric field can oscillate this way or this way, which is in and out of the page. So this dot is an arrow going in and out of the page. But after it hits the surface, it becomes polarized parallel to that surface, meaning the oscillations in this direction get killed off, and the oscillations that are parallel to the surface will remain. So it turns out that when the angle of incidence, the angle that the incident wave is coming in at, is greater than or equal to something called Brewster's angle, then the reflected light becomes completely polarized. So if this wave comes in at an angle greater than or equal to theta b, Brewster's angle, then the outgoing wave is completely polarized, again, along a direction that's parallel to this surface. So Brewster's angle is given by this equation here. Tangent theta b is equal to N2 divided by N1. So this is not an equation we're going to derive. You have to get pretty deep into the equations of electricity and magnetism to really see where this comes from and why the light becomes polarized. So for us, this is going to be an experimental fact. So one really clear example of polarization by reflection is shown down here. We have two different pictures of the same lake. One of them, the one on the left, is taken with no filter in front of the camera. The other one is taken with a polarizing filter placed in front of the camera. Now the difference is pretty clear. In the first picture on the left, it's a little bit hard to see underneath the surface of the water, and that's because there's so much reflected light coming off the surface of the water into the camera that it's obscuring the light coming from under the water. Whereas in this case, it's pretty easy to see what's going on under the water. The reason for that is when light reflects off the surface of the water, it becomes polarized, as we just said. So if we can filter out that polarized light, then we can basically eliminate the light that's reflected off the surface of the water. And that's what we get here. So we're seeing very little light reflected off the surface of the water because we're filtering it out. And so what we see is the light coming from underneath the surface of the water much more clearly. Okay? So you can use polarizing filters to sort of eliminate glare, to eliminate too much reflected light in your images. And so let's do a quick calculation. What is Brewster's angle for light that travels through air and then reflects off the surface of water? Now, to do this calculation, we need to know that the index of refraction of water is 1.33. Remember, Brewster's angle is the angle of incidence that the light wave comes in with, such that the reflected light is completely polarized. So pause the video, try to work this out, the equation's given here, and then come back to it when you have your answer. So again, the picture looks something like this. We have the interface between two materials. We have air up here, water down here. For air, the index of refraction, N1, is equal to 1. Down here, the index of refraction is 1.33 for water. So we have an incident light wave coming in. We measure its angle, as always, with respect to this normal line. And then we have the outgoing wave like this. Now the idea is the incident wave is unpolarized, but the reflected wave is polarized. So the angle of incidence that we need to make this work is Brewster's angle, theta b, where tangent theta b is equal to N2 over N1. So theta b is equal to inverse tangent N2 over N1, which is the inverse tangent of 1.33 divided by 1. So if you punch that into your calculator, you'll get about 53.1 degrees. Okay, so that's Brewster's angle for a light wave traveling from air and then reflecting off water. Okay, so we can take what we've learned about polarization by reflection to understand how sunglasses work. Now, sunlight, that is light coming directly from the sun, is unpolarized. But if sunlight reflects off of a surface, it can then become polarized. So specifically, if we're talking about a horizontal surface, like the surface of a lake or the ground, something like that, after sunlight reflects off the surface, it's going to become horizontally polarized. Remember, it becomes polarized parallel to the surface itself, so it will be horizontally polarized. So we have unpolarized sunlight coming in, reflecting off a flat surface, and then after that, it becomes horizontally polarized. So we indicate that by showing the vertically polarized part is getting a lot smaller, it's being killed off, but we keep the horizontally polarized part. Okay, now sunglasses are fitted with polarizing filters that block this horizontally polarized light. So the vast majority of the light that's reflecting off of these flat surfaces is horizontally polarized. So if you have the right kind of filter that blocks out this type of light, then you can greatly reduce the intensity of that reflected sunlight that would be coming into your eyes. And that eliminates glare, that helps you see more easily. So to do this, we want our sunglasses to have filters with vertical transmission axes, because if I have horizontally polarized light that I want to filter out as much as possible, then I should have a vertical transmission axis in order to do that. And so basically that's all that we have in terms of sunglasses, just vertically oriented filters to block out the horizontally polarized reflected light. So that's going to be it for this video. As always, I have practice problems at the end of each lecture, so as you study for the test, check out these problems, do them for extra practice, and go on Canvas to see my solutions so you can check to see that things are going right. So we'll end this video here. So I'll see you in the next one, but as always, take care, be safe and be healthy out there. See you later.